always we ask ourselves, when we will have a commercially viable quantum computer? Would it be in 5 years, 10 years, 100 years from now? So the answer is not in 2030 or 2035, but next year, according to IBM, in 2026, where IBM has made significant strides in quantum computing, and with their new advancement in error corrections, but also in post-processing, hybrid workflows of quantum and classical resources, they are on track to deliver a solution that can be used now, not in many years. IBM has a strong position in the quantum computing market. Their roadmap is one of the most leading ones in the quantum computing market. And there are several other companies that also are doing hard work and try to make significant contributions. However, with the recent announcement of IBM about the possibility of having a commercially viable quantum computing next year in 2026, leveraging their new hardware and also the software capabilities enhanced with their new error correction techniques like circle codes, for example, and the development of hybrid workflows. IBM is well positioned to lead the market and provide solutions that can be used to deploy and try several use cases in the quantum computing space. And this is very important because it's expected from the market is to use something from quantum computers and try more and more use cases on it. So this is raises the bar of the challenges on other companies and the hardware providers worldwide to keep up with the pace of innovation and also provide solutions that also can be used now or in 2026, but not in 10 or 20 years. Quantum computers now can appear like a watch. Each watch has its own mechanism of ticking the time. Some watches are more accurate than others. Some have more features like sport tracking, heart rate monitoring, and so on. And similarly, quantum computers can have different architectures and capabilities. But the key is to have a commercially viable solution that can be really used to deploy use cases. Examples of quantum hardware include superconducting qubits, trapped ions, neutral atoms, and photonic quantum computers. Each has its own advantages and disadvantages. For example, the coherence time of the neutral atoms is longer than superconducting qubits. However, the set of native gates in neutral atoms is smaller comparing to the superconducting qubits. Also, superconducting qubits have more capabilities in applying it to qubit gates, for example. So we can say that the superconducting qubits have a larger set of native gates, which allows for more complex operations to be applied, but their coherence time is shorter. Another example would be comparing the photonic qubits with superconducting qubits. Photonic qubits have longer coherence times. Virtually, it should be infinite. Photonic qubits are just the photons, and there is no crosstalks between qubits, so they cannot impact, they have less impact of one another, but also they are more prone to the environments. They have also the ability where single qubit rotation gates can be implemented with high fidelity. However, two qubit gates, which are responsible for entangled qubits, are more challenging and probabilistic in nature in photonic qubits. So we can say that IBM bets on superconducting qubits, which is sort of can provide intermediate solution, and they have a larger set of native gates, and they are almost universal, and they can be used to implement gate-based digital quantum computing algorithms. Maybe it is not the best architecture for all use cases in the market, as I have said earlier. However, the magic comes from the hybrid workflows. IBM leverages their new approach of quantum-centric supercomputing, where quantum algorithms are executed using software which optimizes the use of CPUs, the GPUs, but also the quantum processing units to provide the solution that can be used now. So when a user can use this, there is this hybrid workflow which combine both architectures from the classical processing units and the quantum processing units, and they can execute the use cases leveraging the idea of quantum-centric supercomputing capabilities. That's also enables and optimizes the distribution of quantum steps and enabling parallelization of the quantum algorithms in the steps on the quantum hardware. So you just can get more from the quantum hardware leveraging the optimization that happens from the software side and the kind or the tightly integration between the quantum computing resources and the classical computing resources, it's what gives this added value of you get one good package that you can use to execute your use case. Okay, so furthermore, IBM with their new approach of error correction, leveraging modular quantum computing based on bivariate bicycle codes, they are going to potentially enable a commercially viable quantum computer next year in 2026, just by working around the optimizations and the way that the error correction is done. So this gives rise for a significant milestone in the quantum computing space. And here is the thing. The question becomes, how about the other vendors? How they are gonna navigate the quantum computing space? Can other hardware providers of different architectures cope with the pace of that, providing the integration or the integrated solutions that can be used now in the cloud services and the hybrid workflows, and not waiting for the perfect quantum hardware to be available in 2026 or maybe in 2030 or 2035. So here is what I mean by this. IBM, as well as Google, Microsoft, and other similar companies have their own resources to develop their own hardware and software solutions. They can provide, or they have the capabilities to provide similar offerings, including the quantum hardware with integrated solutions involving error correction, but also optimized hybrid workflows. Other companies who have huge investment portfolios also can do similar offerings because they need to enlarge their teams. They can hire a lot of software engineers on board, and also they can offer their hardware through cloud. We have examples like Senado, for example, and other companies. However, when we come to the medium and the small quantum hardware provider, the challenge becomes how to provide similar offerings without the same level of resources, without having this big ecosystem around the company that provides huge resources to provide the offerings. So we have also to note that such companies are doing hard work on their own to deliver their own promised solutions, and they might be focused on such development and solely or maybe partially relying on funding coming from investors to develop their hardware and software solutions. However, the means of running extensive use cases to test their hardware and the software associated with it might not be on the level that can make their platforms commercially viable in the near future. In other words, the long-term market survival of some of the hardware vendors would be potentially coupled with their ability to deliver commercially viable solutions in the near future that can be accessed by cloud and leveraging this kind of hybrid workflows to enable the execution of quantum algorithms based on the quality of the qubits that they have now, not in 2030 or 2035. Otherwise, they have to rely on investments and small deals to keep the company running, hoping that the green areas will not dry out before they can deliver the promised solutions. And here the role of partnerships and collaborations become crucial. A lot of companies are doing partnerships and collaborations with different industries, software companies, and research institutions to maintain their cycle of innovation and development. And this would push the market further because the more you have from partnerships with software companies and research institutions, the more you can benefit from their benchmarking for your particular hardware. Our company, for example, Molkit, relies significantly on the role of helping medium and small quantum hardware vendors and providers to develop their own quantum applications and workflows by testing different use cases and providing clear value propositions for benchmarking and optimization. With this, we can help these companies to develop their own quantum applications and workflows, which can lead to commercially viable solutions. In Molkit, we work on different use cases in chemistry because chemistry can help in scalability. You have a way of controlling or understanding the scalability of your qubits because thanks to the Hamiltonians and the building up the Hilbert spaces required to solve a particular molecular chemistry to solve or to compute a particular spectra of a molecular system. With this, we can systematically study the quality and also your hardware capabilities pertaining to a particular or a set of use cases that can be relevant to this particular hardware. We have seen a couple of examples that have been published in the market to work on a particular quantum chemistry problem. We see it with more and more from the publications on arXiv, how such use cases are really crucial to understand the capabilities of the hardware, but also to reveal what will be the optimal setup to use quantum hardware integrated with the HPC capabilities to deliver commercially viable platform, which can be used to execute different use cases in the cloud and help other vendors and make your company or this particular hardware provider to shine and show up commercially viable platform that can be used in 2026 and cope with the leading roadmap in the quantum computing space. So if you'd like to try out any use case in chemistry or in physics or in quantum-inspired algorithms, feel free to reach out to us, and then we can scope with you a particular problem that can be useful to you, but also benefit from your hardware and show the unique capabilities about it. Also, we can use this to execute a useful use case and a particular solution that can deliver value to the market. Feel free to reach us.